Hi everyone, today we're looking at question 8 part A of the 2004 unit HSC exam. And back then question 8 was the final question, so you know this one's going to be pretty tough. Part A has two parts. What I'll do is I'll take a look at part 1 and part 2 in separate videos. So this video will be just about part 1. And part 1 wants us to use the formula for the sum of a geometric series to show that the sum from k is equal to 1 to n of z plus z squared plus all the way up to z to the k is equal to nz on 1 minus z minus z squared on 1 minus z all squared times 1 minus z to the n for z not equal to 1. Alright, so I've rewritten up what we're being asked to show. Naturally, with all the z's flying around, you know we're kind of in complex number territory, but actually for this part 1, we don't really need to use much complex numbers yet. That'll come for part 2. Part 1, we're actually told, we're given a hint, kind of the route we need to take. And the question mentions geometric progressions and the sum of a GP. So it's probably worth noting to start that the sum of a GP, I'll say GP for geometric progression, is equal to, and these are formulas you probably would have learned in 2 unit or advanced. Hopefully you've etched them into your memory. But it's a 1 minus r to the n over 1 minus r. And that's for r being less than 1. And it's slightly different for r greater than 1. But the reason I'm focusing on the result for r less than 1 is because I noticed this 1 minus z to the n and 1 minus z. So we're kind of in this r less than 1 territory. Now, if you think somewhat deeply about this, it kind of is arguably problematic because when we look at kind of what we're going to end up with, we're going to have a geometric progression where the first term a is z, and the common ratio r, the amount by which each term grows, is also z because we're multiplying by z each time. We get z squared, z cubed, z to the 4 and so on. So for this to be true, we have r, or in our case z, less than 1. I mean, can you say that a complex number is less than 1? What is the magnitude of a complex number when you've got an imaginary part and a real part? Do you just compare the real parts? Are we saying the real part is less than 1? Are we saying the modulus is less than 1? I mean, what are we really saying? I think it's a bit maybe up for debate, but because the question tells us to do it, you know you're in safe territory. Just do what the question writer asks you to do and see if you can get this result. So that's what we're going to do. So the first thing to follow on from here is to make the point that what's inside the bracket, what's inside the summation here in these brackets, z plus z squared plus all the way up to z to the k, that, as I mentioned, is a GP. Itself, it's a GP where basically the first term a is z, and our common ratio is z as well. And n, the number of terms we've got, well, in this case, we've got k terms. So if I kind of insert all that into this result, we get a, or z, 1 minus r, which is z, to the n, which in our case, we've got k terms here. And this is where it can get a bit confusing. We're dealing with n's and k's all over the place. So you've got to be really careful. But here, for this bit that we're specifically thinking about, there's k terms, so we put a k, and then divided by 1 minus r, which again is z. So that's the bit on the inside. And that's, I think, the key. Now, if you were to look at this question and the first thing you were to do was to try and, say, expand this summation, I think you'd end up going down a rabbit hole and you'd probably end up with such a mess that it would be very difficult to get this result. Now, if that is something you did, I think from a kind of just exam-taking perspective, it's always helpful to remember that the exam writers, very rarely are they trying to test your ability to kind of go through masses and masses of mathematics really quickly. Whilst all exams are timed, very rarely are they testing you on your speed in and of itself. So if you're finding yourself going down a rabbit hole that just requires loads and loads of manipulations, maybe pause and ask yourself, have you gone down the wrong track here? Because often it's the case that with a bit of thought, the solution is somewhat elegant. Usually that's what question writers are thinking of, particularly when you're looking at the very last question of a 4-unit exam. You kind of can hazard a guess there's some elegant approach there. So if the approach you're taking isn't elegant, maybe stop and pause, maybe even just move to other questions and then come back to it. So in our case, I think the elegant approach is to kind of know that you can evaluate what's inside the summation, put that in, and then see what you get. So that's what we're going to do. We've just worked out this bit inside the summation itself can add up to this using our GP rules. So now we can say, therefore, the sum from k is equal to 1 to n of z plus z squared and so on up to z to the k. Well, that's just equal to the sum from k is equal to 1 to n of this here. So let's put it in. Z 1 minus z to the k on 1 minus z. And here we have a look at this and we think, well, the summation is over the variable k. So anything that doesn't have anything to do with k, we can bring outside the summation. So the first thing I notice is this z on 1 minus z. It's got nothing to do with k, so let's bring it out. Z on 1 minus z times the sum from k is equal to 1 to n of what's left, which is the 1 minus z to the k. Now that, if we have a think about that, well, this 1 we could add up, and then the minus z to the k we could add up. Now if we're going to just add up 1 n times, well, you're just going to end up with n, because it'll be 1 plus 1 plus 1 plus 1 and so on, n times. So we can simplify this a bit more. We can say z 1 minus z, that stays the same. Then we'll have a bracket. This sum from k is equal to 1 to n of 1, we can just simplify to n, minus, and now we've got the sum from k is equal to 1 to n of z to the k. So that's going to be z to the 1 plus z to the 2 and so on up to z to the, z to the k, and we're going up to n, so up to z to the n. Now, does this look familiar? It's pretty much what we started with, but instead of a k, it's just an n. But again, we don't want to get too confused by our k's and n's. It's the same idea, just we just got to be really careful with how we fill out our, or make use of our sum of the GP result. But now we can say, well, that's z on 1 minus z, n minus, and now let's use our sum of the GP again. We've got a GP where the first term, a, is just z again, and then it's 1 minus, and here again our common ratio is z again, and this time our number of terms is n instead of k, so to the power of n, and then on 1 minus r, or 1 minus z, since that's our common ratio. And if you kind of look at the result we're trying to get, we're pretty close here. I mean, this first term nz on 1 minus z, we're going to get there when we expand the brackets. So that's probably the next natural thing to do. Let's expand these brackets. So we'll just get nz on 1 minus z. That looks good. And then we get a minus. And the z times the z will give us z squared. The 1 minus z times the 1 minus z will be 1 minus z all squared. And then we've got our 1 minus z to the n left. And that's exactly what we got as required. Boom! So that's how you tackle that one. As I mentioned, it is possible that you end up going down a rabbit hole if you try and expand this too soon. I think the real key to this question was to almost, you're kind of iterating twice through your sum of the GP result. You're doing it first for what's inside the summation, then you get to here, and then you kind of I guess you just got to think about what you're really dealing with when you're summing things, and you've got to be very conscious of the variable and what can be brought out of the summation, and then you end up getting there pretty without too much effort. And as I mentioned, it's often the case with these exams, you know, it might look a bit scary at first, but the writers probably have some elegant approach in mind. So again, if you're writing pages and pages of working and getting nowhere, chances are you've gone down the wrong track. So hopefully you found that explanation helpful, and I'll move on to part 2 in a follow-up video. All right, tick boom.